What's up, LJ bros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, and today we're going to talk about building an orthogonal basis with Gram-Schmidt process. So let's say, we have some basis, but it's not an orthogonal basis for some subspace. There's a lot of nice properties of having an orthogonal basis that we've been talking about before. So if I have a basis, but it is not an orthogonal basis, what's nice is that I can take that basis and transform it into an orthogonal basis. And we use Gram-Schmidt process to do that. And another nice part about doing this is that we preserve span, so the span stays the same. And let's talk a little bit about this. So the Gram-Schmidt process means that given a basis, vectors x sub 1, x sub 2, so on and so forth to x sub p, for a non-zero subspace, capital W, of vector space Rn, we can define vectors in the following way. V sub 1 is equal to x sub 1. V sub 2 is equal to x sub 2 minus x sub 2 dotted with V sub 1 over V sub 1 dotted with V sub 1 times vector V sub 1. V sub 3 is equal to x sub 3 minus x sub 3 dotted with V sub 1 over V sub 1 dotted with V sub 1 times vector V sub 1, and then minus x sub 3 dotted with V sub 2 divided by V sub 2 dotted with V sub 2 times vector V sub 2, and so on and so forth. We sort of continue this process. We start to see maybe a pattern here. And we build our last vector to the new set as V sub p, and this is given by x sub p minus x sub p dotted with V sub 1 over V sub 1 dotted with V sub 1 times vector V sub 1 minus x sub p dotted with V sub 2 over V sub 2 dotted with V sub 2 times vector V sub 2 minus so on and so forth. We get to our last term, we're still going to be subtracting. This is minus x sub p dotted with V sub p minus 1 divided by V sub p minus 1 dotted with V sub p minus 1 times vector V sub p minus 1. And then this new set of vectors, V sub 1, V sub 2, so on and so forth to V sub p, is an orthogonal basis for W. And in addition to this, like we said earlier, the span of vectors V sub 1, V sub 2, so on and so forth to V sub k is equal to the span of the old set, x sub 1, x sub 2, so on and so forth to x sub k, and that's for k anywhere from 1 to p. So as we're building this orthogonal basis, we are preserving span every step along the way, that's great. It's going to work out really nicely for us. Now let's talk about this a little bit more and sort of get a chance to visualize what's happening. So let's say that I have two vectors giving me a basis, and that maybe they're not orthogonal vectors. I'm going to name them x sub 1 and x sub 2 are my vectors. Now, when talking about them collectively, we would say, well, these vectors are not perpendicular, they're not orthogonal then. But if I just look at one vector out of the set by itself, I can't really say that one vector, if you just give me one vector only, I can't say that one vector is or isn't orthogonal. It's not until I have another vector to compare it with. So when I'm starting to build my set for my orthogonal basis, I get the first vector for free, because this has to be some respective orthogonality. So we'd say, well, I can just take one of the vectors and start my set with that vector, and I like to rename it. So here I'd rename this vector x sub 1 without a loss of generality. It doesn't matter which one you pick on, but I like to just go in order. I would pick this first vector x sub 1 and call it V sub 1. And this can be the first vector in my orthogonal basis in that set, because there's nothing to compare it against, so there's no harm, right? But now what I want to do is I want to build a vector that's orthogonal to this vector, and x sub 2 doesn't seem to be cutting it. Well, how can I get a vector that's orthogonal to this vector x sub 1, which I've renamed V sub 1? Think about the projection. So now if I think about how this is going to look, and this would be the projection, right? The projection is just going to be some scaled version of vector V sub 1, or scaled version of x sub 1, since they're really the same. But if I think about this dotted line leading me to the projection, that's going to be my orthogonal vector. That's going to be perpendicular. So let me do this in a different color. So now if I think of this as my second vector, I can name this v sub 2. So say, okay, so here v sub 1 is my first vector, and perpendicular to this, orthogonal to this, is vector v sub 2. Well, how do I find vector v sub 2? Well, there's a couple things going on here. Let me try to illustrate this with some more colors. So I have the projection. The projection here is going to be in blue. So this is going to be the projection. So this is the projection of vector x sub 2 onto vector v sub 1, or x sub 1. We're calling it v sub 1, so we're going to stick with that new name for it. But if I want to build v sub 2, what is v sub 2? Well, we'll say where v sub 2 is equal to, it's going to be this vector x sub 2 minus the projection. So it's going to be x sub 2 minus the projection of x sub 2 onto v sub 1. And we know how we can actually write this symbolically. We can do much better. So we'll say then v sub 2 is equal to x sub 2 minus this projection of x sub 2 onto v sub 1. That's x sub 2 dotted with v sub 1 over v sub 1 dotted with v sub 1 times vector v sub 1. And that gives me my next vector v sub 2, which is orthogonal to vector v sub 1. So this is my orthogonal vector. So I can go ahead and build out the rest of my set. That next vector is going to be v sub 2, which is going to be x sub 2 minus x sub 2 dotted with v sub 1 over v sub 1 dotted with v sub 1 times vector v sub 1. And those are my two vectors. V sub 1 and v sub 2 are those orthogonal vectors, and this is how we would compute vector v sub 2. Remember, v sub 1 is just one of the first vectors that we're given. We get one of the vectors in the set for free. What about extending this further? What if I want to do this again? So now let's say I have, and try to believe me trying to draw these perpendicular. So let's say I have vectors v sub 1 and v sub 2 already, but then I had some third vector, do that in red, some third vector, which was the vector x sub 3. See, well, this vector isn't perpendicular. It's not orthogonal to these two. How can I get an orthogonal vector? Well, again, think about the projection. If I project, so here the projection then, I'll do that in blue again. So here, this part in blue, so blue is, this is the projection of vector x sub 3 onto the space spanned by already orthogonal vectors v sub 1 and v sub 2. But I want, it's actually this dotted line that I want, and we were doing that in pink before, so I'll switch over to pink and trace over it. This is the orthogonal vector that I want, and this is going to be orthogonal to v sub 1 and v sub 2. This is v sub 3. Well, what is this? Well, we'll say where v sub 3 is equal to, it's going to be x sub 3 minus the projection. X sub 3 minus the projection of x sub 3 onto the space spanned by v sub 1 and v sub 2. And this is going to be a bit more involved because now I'm projecting a vector into a space that's going to be spanned by two vectors, v sub 1 and v sub 2. So how is this going to look? Well, let's talk about it. V sub 3 is x sub 3 minus, and there's going to be a couple of terms in here, but the projection of x sub 3 onto v sub 1 and v sub 2, that's x sub 3 dotted with v sub 1 over v sub 1 dotted with v sub 1 times vector v sub 1 plus, and then the other part of it is x sub 3 dotted with v sub 2 over v sub 2 dotted with v sub 2 times vector v sub 2. And we wouldn't leave it this way because we can distribute that subtraction through. So then sort of finishing this off, we have v sub 3 Spumoni is equal to x sub 3 minus x sub 3 dotted with v sub 1 over v sub 1 dotted with v sub 1 times vector v sub 1, and then bring that subtraction in, minus x sub 3 dotted with v sub 2 over v sub 2 dotted with v sub 2 times vector v sub 2. And this builds now our orthogonal set, our orthogonal basis is given by v1 and v2. We would have got v1 for free. We would have generated v2 already at this point, right? And then v3, even more work to find it, but we can find it. We get this orthogonal basis. And this process continues on and on and on. So I'm not going to keep drawing the visualizations of these, but you can get an idea as to how we would just extend this idea. Even without thinking about it or seeing it, we can imagine how that next part would look, right? So next I would build from v2, v2, v3, and another vector x4. I could build a new vector v4, where v4 is going to be x4, sort of write it down. So if I want to continue this, then I'd say, well, okay, so then v4, if I had another vector x4, would be x4 minus the projection of x4 onto v1, v2, v3. And then it would follow a very similar format to this. So that's our Gram-Schmidt process, building for us an orthogonal basis. Now let's get some practice. Let's see some examples. So here I have the given set is a basis for a subspace capital W. Use the Gram-Schmidt process to produce an orthogonal basis for W. And I like to start, well, you could start by checking that the vectors are not already orthogonal. They aren't. I like to start by naming these. I name them x sub 1 and x sub 2. And now the very first vector for my orthogonal set, so let me write the set actually up top here. So my orthogonal basis, I should have two vectors in the set because I have two vectors that I'm starting with. And I get one of these vectors for free. So this very first vector, x sub 1, I can just pick on this and say, hey, you can be in the set. There's no issue with just one vector until I have a second vector to pit against it. So I'm going to say, let me name this v sub 1. I'm going to rename it v sub 1. And this vector can be in my set. But now I need another vector v sub 2 that is orthogonal to this vector. And x sub 2 is not orthogonal to it, so that's not going to work. But I can use it to find that new vector. So that next vector that I want is v sub 2. I'm going to name it v sub 2. And this is given by, we saw our formula earlier, that's x sub 2 minus x sub 2 dotted with v sub 1 over v sub 1 dotted with v sub 1 times vector v sub 1. Remember, v sub 1 is just a renaming of vector x sub 1. And let me go ahead and find out what this coefficient is first, and then introduce the vectors back in. So v sub 2 is equal to x sub 2 minus, let's do the dot products, x sub 2 dotted with v sub 1, so I'm dotting these vectors against each other. 8 times 3 is going to give me 24, plus 0 times 5 gives me 0, negative 1 times negative 6 gives me 6, and then divided by v sub 1 dotted with itself, so this is v sub 1. If I dot it with itself, 3 times 3 gives me 9, 0 times 0 gives me 0, negative 1 times negative 1 gives me 1. And let's go ahead and see what this is going to look like. So then here, v sub 2 is equal to x sub 2 minus, this is going to give me 30 over 10 times v sub 1, or that's going to be x sub 2 minus 3 times v sub 1. And now I can introduce the vectors in because I want to build this new vector v sub 2. So it's x sub 2 minus 3 times v sub 1. And what was x sub 2? X sub 2 was the vector in the set that I couldn't really use entirely. That's 8, 5, negative 6. And then minus 3 times v sub 1. V sub 1 was the first vector renamed, 3, 0, negative 1. And then I can go ahead and do the arithmetic here. So 8, 5, negative 6. And then here we'll subtract, and I'll bring the 3 in. So that's 9, 0, negative 3. And then what is this going to give me for my new vector v sub 2? Well, 8 minus 9 gives me negative 1. 5 minus 0 gives me 5. Negative 6 minus negative 3, so that's negative 6 plus 3 gives me negative 3. So I get the vector v sub 2 is negative 1, 5, negative 3. So negative 1, 5, negative 3. My final answer should be the orthogonal basis, right? So it isn't just, finding the vectors. I want to actually build a set out of them. So this right here, up at the top, would be my final answer. So I have an orthogonal basis. And I can check, right? Here, if I do the dot product, I get negative 3, 0, positive 3. Dot product gives me 0, and I preserved the span of the set. So very nice. Let's do the same for another example, just to sort of build up some practice. Here I have these vectors that I'm starting with. I'm going to give them nicknames, x sub 1 and x sub 2, and then my orthogonal basis. That I'm building should also have 2 vectors in it. And I get the first vector for free. Now you could pick on the second vector. I mean, if you want to be fancy, do some cool stuff. If you think that's really awesome, then go ahead and do it. Perfectly fine. It's arbitrary how you name these if you want to shuffle them around. Just don't shuffle the entries, but you can pick up and move the vectors in the set. It doesn't make a difference. But you know me, born to be mild, I'm not going to do that. So I'm just going to stick with this first vector, and I'm going to name that one v sub 1, because I'm not really creative. And this is going to be the first vector in my new set, because there's nothing wrong with one vector. I can't say that it is or is not orthogonal. It's not until I compare it against something else. And if I do find the dot product of these 2 vectors, they are not orthogonal, so we're here to fix that. I'm going to need a new vector. I'm going to call that new vector v sub 2. I have to find it. Well, v sub 2 is going to be given by x sub 2 minus x sub 2 dotted with v sub 1 over v sub 1 dotted with v sub 1 times vector v sub 1. I go ahead and build this. Let's build the coefficient first. So that's x sub 2 minus some scaling on vector v sub 1. X sub 2 dotted with v sub 1, so that's going to be 4 times 2 gives me 8. Plus negative 1 times negative 5 is 5. Plus 2 times 1 gives me 2. And then divided by v sub 1 dotted with itself. 2 times 2 gives me 4. Negative 5 times negative 5 gives me 25. And 1 times 1 gives me 1. Let's go ahead and clean this up a bit. So v sub 2 is equal to, it's x sub 2 minus, and here I have 8 plus 5 plus 2, so 8 and 2 is 10, plus 5 is 15. And then here 25, and then plus 5 gives me 30, v sub 1. So this is really going to be v sub 2 is equal to x sub 2 minus 1/2 of v sub 1. If I reduce 15 over 30. And I want to bring these vectors back in because I want to build this new vector v sub 2. So what was x sub 2? X sub 2 was the second vector in the set. That was 4, negative 1, 2. 4, negative 1, 2. And then what about vector v sub 1? Remember, v sub 1 was the renaming of vector x sub 1, and that was 2, negative 5, 1. And here I can go ahead and work through the arithmetic. So just sort of glancing at how the arithmetic is going to look, I'm going to want to think about getting some common denominators. Though maybe not quite for the first entry. I think the first entry is going to be fine. If I look at this, it's going to be 4, and then minus, and then 1/2 times 2 is just 1. So that's going to give me an integer out, no problem. But for the rest of these entries, I think you're going to want to do some work with fractions. So I don't want to alarm you, but I'm going to rewrite negative 1 as negative 2 over 2. And I'm going to rewrite 2 as 4 over 2. Now it's still the same numbers, but they're written as fractions, so I can have a common denominator ready. Because in here, for example, I want minus, and then 1/2 times negative 5, well, that's negative 5/2. And then here, 1/2 times 1 is 1/2. This is just so I can do my arithmetic with my fractions. Let's see what this gives me. 4 minus 1 gives me 3. Careful with the double minus sign. Negative 2 over 2 minus negative 5 over 2, so that's plus. So negative 2 over 2 plus 5 over 2 is going to give me a positive 3 over 2. And then here, 4 halves minus 1 half is going to give me 3 halves as well. So I get this vector v sub 2, which is 3, 3 halves, 3 halves. Now I want to write this into my set because I want that orthogonal set for my orthogonal basis. So 3, 3 halves, 3 halves. And you can check, you can do the dot product of these two vectors, and you'll see that they're orthogonal, that the dot product gives you 0. So this would be really my final answer, is my orthogonal basis that I built with the Gram-Schmidt process. Very cool. Too cool. Let's take a look at another example with just two vectors, and then we're going to see some more difficult examples. But so now I got a set again, and you know what we're doing. We're given these names. It's x sub 1 and x sub 2. I want to build my orthogonal basis. My orthogonal basis should have two vectors in it to win it. And I get the first vector for free. You want to pick the second vector? You could. You want to pick the first vector? You could. I'm going to pick the first vector. You know I'm doing that. And I'm going to rename it. I'm going to say, hey, you know, the name that you were given is cool and everything, but I got an even better nickname for you. I'm going to call you v sub 1. Whoa. And you're going to get to be in the set. Whoa. Because you by yourself are not an issue. When I compare you to another vector, that's when we run into a problem, because these two vectors are not orthogonal. So I can't just write that other vector in the set. That's not what I'm wanting. I want an orthogonal vector, so let's build it. I have to build that second vector, v sub 2, where v sub 2 is going to be x sub 2 minus x sub 2 dotted with v sub 1 over v sub 1 dotted with itself times vector v sub 1. And I do like rewriting that formula a bunch because it really helps me remember that familiar formula. We've been doing the projection work quite a bit too, so I think by now we're getting really good at this. Let's find that coefficient. What is x sub 2 dotted with v sub 1 going to look like? Well, 7 times 1 gives me 7. Negative 7 times negative 4 is going to give me positive 28. Negative 4 times 0 is going to give me 0. And then 1 times 1 is going to give me 1. And then in the bottom, I want v sub 1 dotted with itself. So v sub 1 is this first vector. 1 times 1 gives me 1. Plus negative 4 times negative 4 gives me 16. Plus 0 times 0 gives me 0. Plus 1 times 1 gives me 1. Now let me go ahead and clean up that coefficient, and then we can start talking about the vector work. X sub 2 minus, here on top, let's go ahead and say, so we have 28, plus 1 gives me 29, plus 1 gives me 30, plus the remaining 6 is 36, divided by here 16 plus 1 gives me 18 times vector v sub 1. And I can do this division. So v sub 2 then is equal to x sub 2 minus 2 times vector v sub 1. I want to bring these vectors back into play, so I've got little vector boxes waiting for them. But I have x sub 2 minus 2 times v sub 1. What was x sub 2? X sub 2 is the second vector, 7, negative 7, negative 4, 1. And then v sub 1 was a renaming of the first vector, 1, negative 4, 0, 1. Yes. Let's go ahead and work this one out. So v sub 2 is this first vector. I'm just rewriting it. And minus, if I bring that 2 in, I have 2, negative 8, 0, 2. And let's do the subtraction. Really emphasizing we're subtracting away projections. 7 minus 2 is going to give me 5. Negative 7 minus negative 8, that's really negative 7 plus 8, gives me positive 1. Negative 4 minus 0 gives me negative 4. And then 1 minus 2 gives me negative 1. So I have this second vector for my set to complete it. V sub 2, that's 5, 1, negative 4, negative 1. So I want to build that into my set. 5, 1, negative 4, negative 1. And now I have my orthogonal basis. And remember, you can check these. You know how to check to show that something's orthogonal with two vectors. It's very fast. You can have 5 minus 4 plus 0 minus 1. 5 minus 4 minus 1 does give me 0 for the dot product. So we're doing it. Looks great. Okay, let's go ahead and kick things up a notch. So I want to find an orthogonal basis for the column space of this given matrix. So what I want to do to start is I want to think about these columns as vectors. So I would go so far as to even write them out in a set. Though you maybe don't need to do this if you're just looking at them. If you can sort of do it mentally, separate them as column vectors. But this is my starting set of vectors. And I have a column vector 3, 1, negative 1, 3. I have another vector negative 5, 1, 5, negative 7. And I have a third vector 1, 1, negative 2, 8. And these were given names to start with of x sub 1, x sub 2, and x sub 3. But these are not going to be orthogonal pairwise. And I could check them to show that, to ensure that. But, you know, still want to build my orthogonal basis anyway. So my orthogonal basis, I'm going to write it right next to it, should also have 3 vectors. It's going to have the same span too. And I get one of the vectors for free. So I'm going to say, hey, this first vector, by itself, it is not an issue. It's not until I introduce other vectors that we can judge it. But I'm going to call this first vector v sub 1, give it a nickname. And hey, you get to be in my set. That's 3, 1, negative 1, 3. But now we want to build the next vector. We've done this quite a bit as well. So we know how to build this. Vector v sub 2 is going to be x sub 2 minus some scaled version of v sub 1. Remember what this is supposed to be on top. It's x sub 2 dotted with v sub 1 over v sub 1 dotted with v sub 1. What's x sub 2 dotted with v sub 1 going to look like? Well, negative 5 times 3 gives me negative 15. Plus 1 times 1 gives me 1. 5 times negative 1 gives me negative 5. And negative 7 times 3 gives me negative 21. And then divided by v sub 1 dotted with itself. So that's the first vector. 3 times 3 gives me 9. 1 times 1 gives me 1. Negative 1 times negative 1 gives me 1. And 3 times 3 gives me 9. Let's go ahead and see what this coefficient is going to look like. So v sub 2 is equal to x sub 2 minus, and here up on top, it's okay, negative 15 minus 5 is going to give me negative 20. Negative 21 plus 1 is another negative 20. Negative 20 and negative 20 gives me negative 40. Divided by 9 and 1 is 10, and then again, so 10 and 10 gives me 20 times v sub 1. So then for v sub 2, this is equal to vector x sub 2. We have minus and negative is plus. 40 divided by 20 gives me 2 times vector v sub 1. And I want to start introducing these back. So what was vector x sub 2? That was the second vector, negative 5, 1, negative 5, 1, 5, negative 7. And then v sub 1 is this first vector, 3, 1, negative 1, 3. I want to work through the vector arithmetic. So if I'm doubling that vector v sub 1, so it's plus then the vector 6, 2, negative 2, 6. And I can build this vector v sub 2. So here, negative 5 plus 6 gives me positive 1. 1 plus 2 gives me 3. 5 plus negative 2 gives me 3. And negative 7 plus 6 gives me negative 1. So that vector v sub 2, my second vector, is 1, 3, 3, negative 1. 1, 3, 3, negative 1. I can go ahead and check these are going to give me something orthogonal. I get 3 plus 3 plus negative 3 plus negative 3. So the dot product so far is looking good. You can check along the way. I think it's good to do that to make sure that Everything's going the way that you want it to. Now I need a third orthogonal vector. Let me switch colors for this so it doesn't all run together. But now I need vector v sub 3. Remember from our formula before, v sub 3 is going to be given by x sub 3 minus the projection of x sub 3 onto v sub 1 and v sub 2. But if I were to expand that out and distribute the minus sign through, that's x sub 3 dotted with v sub 1 over v sub 1 dotted with v sub 1 times vector v sub 1, and then minus x sub 3 dotted with v sub 2, now that I have it, divided by v sub 2 dotted with v sub 2 times vector v sub 2. And I want to go ahead and build this out. So v sub 3 is equal to x sub 3 minus some scaled version of v sub 1 minus some scaled version of v sub 2. But let's find these dot products. What is x sub 3 dotted with v sub 1? Well, let's go back. X sub 3 is the last vector in our original set. V sub 1 was a renaming of the first, so we're sort of skipping over and finding the dot product. So I'm going to have 3 plus 1, and then what's the rest of it? Negative 2 times negative 1 is 2, and 8 times 3 is 24, so I get, and then 2 and 24. And then divided by v sub 1 dotted with itself. We did already compute this, but just to sort of show again, it's going to be 9 plus 1 plus 1 plus 9. And then for the other coefficient, I want x sub 3 dotted with v sub 2. Okay, so v sub 2, I have to look in my new set for that. I'm still waiting for v sub 3, but so I want x sub 3 dotted with v sub 2, so I'm kind of skipping over to this other set. So that's 1 times 1 is 1, 1 times 3 is 3, so far I have 1 and 3. And then negative 2 times 3, so that's negative 6. And 8 times negative 1 is negative 8. So I got negative 6 and then negative 8. Then divided by v sub 2 dotted with itself. So I'm looking in this new set, v sub 2 dotted with itself. That's going to give me 1, 9, 9, 1. I can actually look here for v sub 2 as well. It's a bit closer there. Let's go ahead and clean up these coefficients. So v sub 3 is equal to x sub 3 minus, let's see what we get here. So 2 and 1 is 3, 3 and 3 is 6, 24 and 6 gives me 30, divided by 9 plus 1 plus 1 plus 9 is 10 and 10 is 20, times vector v sub 1, and then minus negative 8 and negative 6 is going to give me negative 14, plus 4 gives me negative 10, over, again, 10 and 10 is 20, times v sub 2. So v sub 3 is equal to x sub 3 minus, if I'm reducing, that's 3 halves times vector v sub 1, minus a negative is plus, this is going to be 1 half vector v sub 2. Now let's bring these vectors back in. So what was x sub 3? X sub 3 was my third vector of the original set, 1, 1, negative 2, 8. What was v sub 1? V sub 1 was the renaming of my first vector, but I can actually look in this new set, 3, 1, negative 1, 3. And v sub 2 is the second vector in my new set that I'm building, that orthogonal basis. V sub 2 is 1, 3, 3, negative 1. Let's bring in those coefficients and go through some arithmetic here. So v3 is vector 1, 1, negative 2, 8. I'm going to bring in the minus sign as well as the 3 halves so that I can just be adding vectors. Negative 3 halves times 3 is negative 9 halves. Negative 3 halves times 1 is negative 3 halves. Negative 3 halves times negative 1 is positive 3 halves. And negative 3 halves times 3 is going to give me negative 9 halves again. And then plus Let me bring the 1/2 in. So I'm going to have 1/2 times 1 is 1/2. 1/2 times 3 is 3/2. And then again. And then 1/2 times -1 is -1/2. Now I want to add these vectors together. I'm going to wait on the first vector. I'm going to add these second two vectors together first. They already have common denominators. I'm hoping that I get something nice out of those. Let's go ahead and add those together. -9/2 plus 1/2 gives me -8/2, which is -4. -3/2 plus 3/2 just gives me 0. 3/2 plus 3/2 gives me 3 whole, or just 3. And then -9/2 plus -1/2 is -10/2, which is -5. And then now I can go ahead and add these vectors together to get v sub 3. 1 plus -4 gives me -3. 1 plus 0 gives me 1. -2 plus 3 gives me 1. And 8 plus -5 gives me +3. So this is my third and final vector for that new orthogonal set, vector v sub 3, where v sub 3 has entries -3, 1, 1, 3. So -3, 1, 1, 3. And now I could check and show that all of these vectors, v1, v2, and v3, are orthogonal pairwise. This is my orthogonal basis with the same span as the original set. So very, very nice. And we say, hey, thanks, Gram-Schmidt. Let's take a look at another sort of similar application of this, QR factorization. This is going to be our last example for the section. We'll move on to some new stuff to finish off the chapter. But for QR factorization, we have if A is an m by n matrix with linearly independent columns, then A can be factored as A equals Q times R, where Q is an m by n matrix whose columns form an orthonormal basis for the column space of A, and R is an n by n upper triangular invertible matrix with positive entries on its diagonal. And we have an example. We have a matrix A that's given. We would like to find an upper triangular matrix R such that A is equal to Q times R, and then we're going to talk about how we can check our work. Now, let's build Q first. Q is going to be an m by n matrix whose columns form an orthonormal basis for the column space of A. So let's start with, maybe not orthonormal, let's start with orthogonal. Let's get an orthogonal basis for the column space of A. And this is our Gram-Schmidt process. So here I'm starting with this matrix A. Think about these as vectors. I'm going to name the vectors x sub 1 and x sub 2. And that first vector x sub 1, I'm going to nickname it v sub 1. So my orthogonal basis I get one of the vectors for free. And I'm just going to pick on that first vector, which is 5, 1, -3, 1. But I have to build my second vector. So how's v sub 2 going to look? Well, it's going to be x sub 2 minus some scaling of vector v sub 1. What should go on top? Well, that's x sub 2 dotted with v sub 1. So 9 times 5 gives me 45, plus 7 times 1 gives me 7, plus -5 times -3 gives me 15, plus 5 times 1 gives me 5. And then divided by v sub 1 dotted with itself. 5 times 5 is 25, plus 1 times 1 is 1, -3 times -3 is 9, and 1 times 1 is 1. Now I want to go ahead and find out what this coefficient is, and then I want to build this new vector. So v sub 2 is equal to x sub 2 minus, what about on top here? So here I'm going to have 45 and 5 is going to give me 50, plus 15 is 65, 65 plus 7 is going to give me 72, divided by 9 plus 1 is 10, 10 and 25 is 35, plus 1 is 36, times v sub 1. And that's going to divide cleanly. So let's build this new vector. V sub 2 is x sub 2 minus 2 times v sub 1. Right? 72 over 36 gives me 2. So what was x sub 2? X sub 2 is my second vector here, 9, 7, negative 5, 5. And what was v sub 1? V sub 1 was the renaming of that first vector, 5, 1, negative 3, 1. And here, if I go ahead and expand this out, bring the 2 in. That's 10, 2, negative 6, 2. Let's do the subtraction. 9 minus 10 gives me negative 1. 7 minus 2 gives me 5. Negative 5 plus 6 gives me positive 1. And then 5 minus 2 gives me 3. So negative 1, and this is v2 then. Negative 1, 5, 1, 3. Negative 1, 5, 1, 3. Now this is an orthogonal basis. An orthogonal basis. But I want, if we remember from Q, I want to build Q as an orthonormal basis. I want the columns of Q to give me an orthonormal basis for the column space of A. Now for an orthonormal basis, I need to take these vectors and I need to make them into unit vectors. So I have to find their length and divide by their length. So if I find the length of this first vector, and it's not, I call this v sub 1, I guess, and v sub 2, but it's not quite what I want yet. I'll do the work up here where I have some space for it. The magnitude of vector v sub 1 is going to be the square root of, and then think about dotting the vector with itself. So 5 times 5 is 25, 1 times 1 is 1, negative 3 times negative 3 is 9, 1 times 1 is 1. So that's what the square root of 36 gives me 6. But then if I find the magnitude of that second vector v sub 2, I think you'll be surprised to see that it's not really different, right? Negative 1 times negative 1 is 1, 5 times 5 is 25, 1 times 1 is 1, 3 times 3 is 9. It's really sort of the same sum, so I get square root of 36, gives me 6. So both of these are not unit vectors, and they both have length 6. So if I'm going to build an orthonormal basis, I'm going to take these vectors that I have, and I'm going to divide by the length of the vectors. So what was v sub 1 was 5, 1, negative 3, 1. I have to divide everything by 6. And then v sub 2, I can actually look here, I'm sort of cheating, but that's negative 1, 5, 1, 3, and that also had length 6 for a vector, so I have to divide everything by 6. Now, I wouldn't worry about reducing. I'm looking at it too. I see negative 3 over 6 and positive 3 over 6. You know it's going to reduce to 1/2. But it's actually, for what we're going to probably do next for the arithmetic involved, I think it's better to leave it unsimplified. So I'm going to build my matrix Q. Matrix Q is really the same size as matrix A, but now the columns are going to be orthonormal columns. So I'm just going to make these columns of a matrix. But now I want to find matrix R. And R is supposed to be some square upper triangular matrix, right? We described it before. So R is an n by n upper triangular invertible matrix with positive entries on its diagonal. So there's a lot of details about it there. There's something very nice that I can go ahead and talk about next. And I want to actually show, or at least show a little bit about the result. Let me actually write it up top here, and then I'm going to use the space above to actually discuss it a bit further. So since Q, I'll write this out in words, since Q is what we would call there's actually sort of a specific nomenclature for this. Let me write it this way, because I don't want to say something that might be confusing. Since Q is made from orthonormal columns, Q's inverse is equal to Q transpose. And there's a couple things I want to just mention in passing we would actually refer to this as an orthogonal matrix. I think it's a confusing nomenclature. In order for something to be an orthogonal matrix, the columns have to be orthogonal and unit vectors. So, you'd say, well, why didn't we just call it an orthonormal matrix? Well, I'm not really in charge of the nomenclature for these things, so it wasn't my fault. But we would consider it to be an orthogonal matrix. To be an orthogonal matrix means the columns have to be orthonormal, which I think can be a bit misleading or frustrating at first hear of it, but that's what we're talking about. But so I'm just going to word it this way so there's no ambiguity and that we're not confused, though this term is going to come up later. Since Q is made from orthonormal columns, Q's inverse is Q transpose. And let me show why this is. I got this lovely real estate up here. So let A have orthonormal columns, v sub 1, v sub 2, so on and so forth to v sub n. And I'm just picking on any matrix. I'm not trying to talk about the A that we're working with in the example that we're working with. I'm trying to just give a general idea here. So A is a matrix where the columns are v sub 1, v sub 2, so on and so forth to v sub n. And these are orthonormal columns, meaning they're pairwise orthogonal, and they're all going to give me unit vectors, that their length is 1. Then notice that A transpose is going to be a matrix where these column vectors are now row vectors. So v sub 1, v sub 2, so on and so forth to v sub n. These are row vectors. So we could say this have sort of the orthonormal rows. Well, now think about what A transpose times A is going to look like. So A transpose times A means I'm taking my transpose, where now all of my columns are rows. Those orthonormal columns are now row vectors of A transpose, times matrix A, where there I have the column vectors. I'm going to get a really nice result out of this in the space that I have, hopefully. Let's just sort of talk a bit about it. Go through the row column rule. I'll try at least right here. So I'm going to fix this first row, which is row vector v sub 1. I'm going to go through the column. I'm going to move through the columns of A. So v sub 1, I think of it like a dot product. V sub 1 dotted with v sub 1, since it's going to be orthogonal and unit vectors, that's going to give me 1. I'm dotting it with itself. But for the rest of this, v sub 1 dotted with v sub 2, since it's orthogonal, gives me 0. And the next would be, for example, v sub 1 dotted with v sub 3, that would give me 0, it's orthogonal. So on and so forth. V sub 1 dotted with v sub n is going to give me 0, it's orthogonal. But then we move on. We try to do the next, try to fill in more of this A transpose times A. If I go down to the second row, which is v sub 2, and then back through the columns, v sub 2 dotted with v sub 1 gives me 0, they're orthogonal. V sub 2 dotted with v sub 2 gives me 1, because it's the same vector, and it's a normal vector, it's a unit vector. V sub 2 dotted with v sub 3 would give me 0, so on and so forth. V sub 2 dotted with v sub n would give me 0. These are orthogonal vectors. And then so on and so forth. If I go all the way down to v sub n, we'll say, well, v sub n dotted with v sub 1 gives me 0, it's orthogonal. V sub n dotted with v sub 2 is going to give me 0, it's orthogonal. V sub n dotted with v sub 3 is going to give me 0, it's orthogonal. So on and so forth. But then when I get to the very end, v sub n dotted with itself, it's not going to give me 0. And since these are unit vectors, it's going to give me 1. And this is the identity. This is the n by n identity. So what we're saying is A transpose times A gives me the identity, which means that A transpose is A's inverse. So since, and we said that A was made of orthonormal column vectors, so this gives us a really nice result. Now, with our QR factorization, so I used A as an example, but Q in particular is the matrix that is orthonormal. Well, actually, we call it an orthogonal matrix, but the columns are orthonormal. Since the columns of Q are orthonormal, then Q transpose is Q's inverse. which allows us to find this matrix R. So our factorization that we're looking for is A equals Q times R. So okay, so let's get back to work then. A is equal to Q times R. But since Q's inverse is Q transpose, I can do A equals Q times R, and I can multiply by Q transpose on both sides. And here I have Q transpose times A is equal to, now Q transpose times Q gives me the identity times R, which means that Q transpose times A is equal to R. And now I know how I can actually build this matrix R for my QR factorization. It's just Q transpose times A. So R is equal to, I want Q transpose times matrix A. Well, what's Q transpose? Well, what was Q? So here's Q. I want to transpose it, meaning this column becomes a row. So 5/6, 1/6, negative 3/6, 1/6. So this first column becomes my first row, and then second column becomes my second row, negative 1/6, 5/6, 1/6, 3/6. And then I need times A. So Q transpose and then times A. A was the original matrix, which we haven't talked about for quite a bit now, that had columns 5, 1, negative 3, 1. And then the second column that was 9, 7, negative 5, 5. And I want to multiply these. So here it's kind of good that I didn't reduce the negative 3/6 and the positive 3/6, because I actually get like fractions for this. I can go ahead and do the multiplication. If you want to think about sizing first, this first matrix here is a 2×4. Times here I have a 4×2. So this result is going to give me a 2×2 for matrix R. But I'm going to give lots of space for this so I can think about the arithmetic. It's a 2×2 matrix. Let's talk about what the entries are going to look like. Think about the row column rule. And since everything is going to sort of have this denominator of 6, I'm just going to get a big old fraction bar ready. We're going to say, okay, 5 times 5 is 25, plus 1 times 1 is 1, negative 3 times negative 3 is 9, 1 times 1 is 1. And I'll clean this up later. And now I'm going to have another fraction all over 6. So first row, but now second column. 5 times 9 is 45. 1 times 7 is 7. Negative 3 times negative 5 is 15. 1 times 5 is 5. Let's fill up this second row here. So now we're going to go to the second row of Q transpose and then the first column of A. And again, get the fractions ready. Negative 1 times 5 is negative 5. 5 times 1 is 5. 1 times negative 3 is negative 3. 3 times 1 is 3. So you can see probably what's going to happen there. And last one. So second row, second column. Negative 1 times 9 is negative 9. 5 times 7 is going to give me 35. 1 times negative 5 is negative 5. 3 times 5 is going to give me 15. Let's build matrix R. Let me use this space over here, actually. So 25 and 1 and 9 and 1 give me 36/6. This is familiar, right? 45 plus 7 plus 15 plus 5. We said that gave us 72/6. This here, negative 5 and 5, negative 3 and 3 give me 0/6. And here, this last one, 35 minus 5, gives me 30. And then 30 and 15 is 45. 45 minus 9 gives me 36/6. So then let me just sort of, I'll write it just underneath. Matrix R has entries 6, 12, 0, 6, read off row-wise. And then A is equal to Q times R. So I'll write that above too. A is equal to Q times R. And how is that going to look? Well, Q times matrix R. I just found matrix R. I'll fill that in first. What was Q? Q is my orthogonal matrix with orthonormal columns. So Q had columns 5/6, 1/6, negative 3/6, 1/6, and then negative 1/6, 5/6, 1/6, 3/6. And then I don't really have room to check it, so we're not going to quite do the check. But what you could do is you could multiply this out. And it's actually not so bad to do. I'll give you a recommendation for the multiplying. Since it looks like everything has this common denominator of 6, factor a 1/6 out of this matrix, and then bring that 1/6 through this matrix here. Kind of bring that coefficient around. And the multiplying is going to go a little bit easier, but you will be able to show that this factorization builds back matrix A. So this is my QR factorization for that matrix A, made possible by the Gram-Schmidt process. Hey, I hope you liked this. I hope you thought it was cool. You thought it was fun. I hope you had a good time. No matter where you are and what you're doing, remember to always keep learning, keep dreaming, and follow your heart. And hey, don't go anywhere. We're going to do more stuff with math and cats coming up, and I will see you next time.